Yeah. Okay. Good morning, everyone. My name is Lola, and I'll be exploring studies on the optical spectra and conductivity of transition metal copper complex. A little background: transition metal complexes are also referred to as coordination compound of complexes, which consist of a central metal atom connected to one or more ligands. Transition metal complexes have high electrical and thermal conductivities, and they have a redshifting property, which is the ability for them to show up in the near infrared region. They are useful for both industrial and biological applications. However, the challenge is most of the investigated photoactive transition metal complexes are low in the Earth crust, and um, the TMCs which show up in the near infrared regions have been under pursuit because of limited understanding of molecular interplays. However, the goal is to synthesize new complexes from Earth abundant elements with knowledge known from transition metal complexes like iridium and platinum. How I'm going to be doing that is to rationally select the substituents on the ligands. The metal that I was using for this project is copper. It's abundant in the US and is not reported toxic or carcinogenic. So the main goal is to explore the optical conductivity properties of copper complexes. For this project, I had explored two methods. Um, I used VAS for the DFT. Sorry, there's a mistake in my there's a mistake in this slide. The mixed basis set was for the Gaussian. So I had done TDDFT and DFT for this project. Here is a view of what the complex looks like. And for the sake of DFT, the major ligand on top on here is the carbonitrile. Now, after carrying out vast calculation using density functional theory, I came up with this result. I checked for the energy changes in my model by exploring varying number of electrons. So what I did was I changed the different number of electrons for each of the model, and I tried to monitor what the energy changes were like. And I observed that stability was achieved when the model was reduced to 167 number of electrons. The neutral electrons contained 166 electrons. But then I realized that the energy began to surge as I increased more of the electrons. One of the other parameters I looked into was density of states, which was the spin polarized density of states for both the neutral and the anion. The anion in this case now is the one that I achieved stability for, which is the one with 167 number of electrons. Now, this is what I observed. Right here is the density of states for the neutral, and here is that for the anion. When I checked the band gap in the alpha region, I got a band gap of 1 electron volt. For the anion, I got something lesser, about 0.25 electron volts. But when I checked for the band gap in the beta position, it was around the same value, which was 0.25. So I was able to conclude from this that the anion state will be a better conductor. Although the neutral state isn't so bad because I mean it falls between the range of the band gap expected for a conductor, which is about 1 to 3 electron volts. One other parameter that I also explored is the quotient orbital because I wanted to look at the metal to ligand interaction. Now, this is what I observed. For the neutral model, which contains 166 electrons, there was a significant metal to ligand transfer, and I was able to conclude that there is quite a level of coordination between the central metal ion and the ligand, which is great for optical activity. However, for the stable anion, I observed a ligand to ligand charge transfer. The other parameter that I also explored was absorption spectra. Now, this is what I noticed on checking for the spectra. The anion, which is the one which I considered stable with the 167 electron, it showed up in the MIR region, which is the mid-infrared region, with a wavelength of about 3,800 nanometers and a reasonable level of intensity. But the neutral state showed up at about 5,200 nanometers, but with a higher intensity. And I was able to conclude that the neutral state of this model will emit light the brightest compared to the neutral state. Now, remember that the main ligand that I used for this DFT was the carbon nitrile. However, for the TDDFT, this was what I did. I sort of like changed the subsequence on the model. I explored for the carbon nitrile, hydrogen, NO2, NPH2, and OCH3. And this is what I observed. The carbon nitrile, NO2, and the OCH3, they exhibited brighter states in the NIR region, and the carbon nitrile showed up with the highest intensity, which sort of like agreed with the result from the DFT. Now, for my conclusion, the spin polarized spectrum of the neutral state emitted more light in the MIR region compared to the anion. With the TDDFT model, this subsequent CN, OCH3, and NO2, they emitted light with about reasonable intensities in the NIR region, even though the subsequent with the NPH2 and hydrogen showed up with slightly higher intensities. So I'm able to conclude that my copper complex will perform better in the neutral state, although it might be more expensive because it has like a higher wavelength compared to the anion state. Yeah, but I mean, at the end of the day, I concluded that it will be a better material for emitting in the NIR region. Thank you.
Please join me in thanking Lola.